Yeah, thank you, Kelly, very much
Yeah.
for giving me a
Yeah.
chance to speak here, even though I know nothing at all about the subject. And so I hope that everybody will bear with me. If you have any questions, please do ask. If you think I'm making a mistake, then please do definitely speak up. Okay, so yeah, so going back to the very first lecture, which I will need to visit again and again as we go through this. This is my understanding that the first three items that were introduced, that's what we require, that's what is our goal. And geometry is going to be in the service of complexity theory. But there was a fifth item, and the first speaker said that there were 5 separate beginnings, as it were, that you could start from those 5 points. So we are going to begin with the fifth one today. It could really be a new beginning. So that is going to be representation theory, which really is just linear algebra. So if you have not seen any group actions or representation theory, then there's going to be several words introduced, and I may indulge in some math speak. But if you're unhappy with that, then just focus on definitions. That's it. And examples. There are going to be a number of examples. And these are concrete examples. So KV has assured me that this subject is extremely concrete. So I've tried to give a number of examples, and I think several of them will be quite profitable to work out. Okay, so that's the plan. And without further ado, let's just start. So a group acting on a vector space is a linear situation. Even when situation is not linear, we like to make it linear in mathematics. This is tremendous payoffs in many cases. But let's begin with a simpler situation where you have a group and it just acts on a set. So I hope that many people have seen this definition. A group acting on a set simply means that there is an action map from G cross S to S. And as is very common in computer science, you can shift your orientation to think of this as a map from G to maps from S to S. Now, elements in the group are all invertible. So actually you land up in the permutations of the set S. And both of these ways of thinking are quite useful. But the first way, that is the action, that gets used much more often. And you have this dot notation. You don't really give a name to this map. If there are several actions, then you just rely on the context to see which action is being talked about. So the pair G comma X just goes to G dot X. And often we even delete the dot, though I will try to be careful and always keep it here. So the fact that this is a group homomorphism means that basically translated onto the left-hand side really boils down to this associativity equation. And you also want the identity element of the group to act as the identity map, just to ensure that everything is invertible when you think of G as acting. So by means of this, every element of G is really just a concrete permutation of the set S. Now, this immediately induces an equivalence relation on the set S on which the group is acting, where if one element of the set is taken by a group element to another one, then I consider those two elements equivalent. This is transitive because of you can act by elements repeatedly, and it is symmetric because the inverse brings you back. So you get equivalence classes and you call them orbits. So the orbit of any element small x in the set S is just entire G acting on that. So let's see some examples of this. And the initial examples are extremely simple, but they're still important. So the very first one is the trivial action of any group on any set. So that just means that every group element acts by identity. G sends every X to itself. So in terms of the group homomorphism, this is the trivial homomorphism where every group element is going to the identity map on the set S. The other one, the next one, which is the defining action of the symmetric group. In this case, Sn just acts naturally on any set of n elements. So what is the action here in terms of a group homomorphism? So this is the other end where the group homomorphism is identity. Okay. So this action is transitive, which means that there is only a single orbit. Every element Vi can go to every other element. And in fact, this is a simple transitive action. So these are very simple things, but as is often the case in mathematics, from simple things and some combinations, you can build quite a bit of complexity. So, so you can get new actions from old. So if a group G acts on a set S, then it will act on ordered pairs, ordered triples. And in general, it will act on lists of elements from the underlying set. You can take lists of a fixed length or have the length vary. And the action is very simple. If you have a list, then a group element is simply going to take every element in the list and act on it individually. Exactly the same way, the group is going to act on subsets of S. You can take all subsets of S, or you can take subsets of S of a fixed cardinality. So for example, just as a small thing, you can see for yourself what would happen. For example, if I take the defining action of the symmetric group, and if I take this n element set, and if I consider the action on the twofold product, then what will be the orbits of that? Okay. So you should see that there are going to be two orbits over there, where the two elements are the same and when the two elements are distinct. And likewise, this last one is actually going to be important for us. So, one thing to say is that the reason why I'm saying this is that this is kind of a toy situation. But when we come to the linear situation, when we talk about representations of arbitrary groups, and even more when we talk about representations of reductive groups, then these themes are going to be repeated. When we consider concrete examples. So this last one is multisets made of elements of S. So that means that an element from the underlying set is allowed to repeat. Okay. And again, every element of G acting on such a multiset or set or list is going to keep the size the same. Right? So you can restrict to a fixed cardinality. Right. So here's a small exercise for you. And if you have not seen this, then it really is worthwhile to do this. Okay. Yeah, and a graph isomorphism problem. So if you are given two graphs, then to see whether these two graphs are abstractly isomorphic regardless of labeling, this is really a question of asking whether two things are in the same orbit of an action, right? So this language is, you can use this language to talk about that. Okay, so if there are any questions, please do stop me. Is everything okay so far? All right, so remember, I cannot see most of you, so please do speak up. But for now, I'll just take it as an okay to go ahead. All right, so now we are come to the situation which is closer to our interest today, which is group representations. Right. So G is an abstract group still, it's any group, but now it is going to act on a vector space. So you still have the same situation as before, an action map from G cross V to V, which satisfies the same properties as before, except when you take the group homomorphism, you are not landing up in arbitrary permutations of the set V, but rather V being a vector space, I want every element of the group to act as a linear map. Okay. And this linear map has to be invertible because the group elements are invertible. All right. Yeah, so this kind of game can be played in a large number of situations, but for us, the group for now is going to be finite. Later on, it will not be. However, the vector space will always be a complex vector space. Linear algebra over, the reason is linear algebra over complex numbers is nice because I can always find eigenvalues. All polynomials have roots. And the fact that the characteristic is 0 will also turn out to be important later on. We can definitely consider infinite dimensional representations later on. They are interesting. But for us, almost always representations will be finite dimensional. Okay. Yeah, so, so I still have not explained why I want to consider this at all. Because remember, until now, for the past 2 lectures, we were really talking about geometry, groups acting on varieties and orbits and their closures. So just bear with me for a moment. So let's just assume that this is going to be interesting. But the question is, for its own sake, how do I analyze group representations? So of course, there is the old way of doing it, which is I just regard V as a set and I see what the orbits are. This is very interesting, especially in our case, this is going to be very interesting, but it is a separate question. For now, I want to consider the linear nature of V, and I want to consider only those, only the linear decomposition of V, as it were. Now, what I mean by linear decomposition, I will make it precise very soon. But I do not want to consider an orbit as a valid thing in this world where I'm in a, that I'm considering now. All right. Yeah. So the question is, so for a group action on a set, the decomposition was very easy, at least, abstractly. Namely, if a group is acting on any set, then it just breaks down as a disjoint union of orbits. Right? So we would like to have something analogous here. So what is a sub-representation or a G submodule of V? It's something that is part of V and it should be stable under the action of G, but now I require it to be a linear subspace. Okay, so that's what I call a sub-representation. Now this word representation is a very odd one, which you have to, if you have to keep talking about it again and again, and especially representation of a group is quite a mouthful. So people often say G module. Anyway, all right. So let's look at some examples. And the very first examples to visit are the ones that we had earlier for group actions. So the trivial action is when G acts again as identity on any element of the vector space. So it is still the identity map. The identity map is linear. Okay. So this may seem really too trivial, but it's actually going to be important for us by the end of the lecture. Now, so there is one interesting thing. It may seem that linear actions are special cases of actions, but you can actually go the other way. You can make any action on a set. You can convert it into a linear action by simply regarding a set on which G is acting to be the basis of a vector space. So by taking finite linear combinations, symbolic finite linear combinations of elements of that set, and the action of X, the action of G on those elements just extends linearly. So I've done it here for the symmetric group action. So the symmetric group is acting on n symbols, which I'm calling V1 up to Vn. Now I can take any finite linear combination of them symbolically, and G will simply act by again permuting the V's. The action will now be a permutation matrix. But since you can define a linear transformation arbitrarily on a basis, this is a perfectly valid way of defining a representation. Okay. Now, one thing I'd like to note, there is another way to think of this process of linearization. Instead of thinking of this as formal linear combinations, you can think of this vector summation Ci Vi as a function that takes a basis vector Vi to Ci. Okay. And this is pretty much the same, but notice one small thing again, which is that if your underlying set on which the group is acting abstractly, if it is infinite, then the two notions, vector space with that set as a basis and all functions, that is different, because formal linear combinations are going to be functions only with finite support. Okay, so just a small point. So this linearization idea is going to be very important for us later on. It will be executed in a different way, but the fact that I can go to functions is a very useful thing. All right. Now, just like given an action on a set, I can get new actions. In exactly the same way, I can get new representations from old. And here are a few simple ways. So if I have a linear action on two separate vector spaces, then I can just put them together as a direct sum. And every element of G, which remember is now acting as a matrix on V and as a matrix on W. I can simply put those two matrices together in a block diagonal form. They do not interact in any way, and I will get a valid representation on the direct sum of V and W. Again, nothing exciting is going on, but we are simply putting some bricks in place for later on. Okay. And we already talked about sub-representations or G submodules, which are subspaces stable under the action. Now, a first slightly interesting exercise. So remember that we had the defining action of Sn on the n element set. If I linearize it, then I can regard this as a representation. And so now the thing is, the old action was transitive. There was only one orbit. But now, if you think about it just for a little while, you will see that there are sub-representations of the corresponding linearized action. Okay? And it is a good exercise, simple but good exercise to figure out exactly what these two sub-representations are. One of them is just going to be a copy of the trivial representation. Okay. All right. So, yeah. And it's a neat thing that not only are there two sub-representations, but actually this representation V is isomorphic to their direct sum. Okay. So when I said is, what I mean is isomorphic to. So there is a natural notion of isomorphism of representations. There is a natural notion of G linear map, which I will not write down. Okay. All right. So with this in mind, I want to revisit this question. A G set can be broken into orbits. Is there any notion, similar notion like that for decomposing a representation into irreducible representations? Okay. So some kind of
there's a question. Sorry,
yes.
Upendra, there's a question in the chat. Maybe you should just look at it.
Right. So
should I read it for you?
Yes, please. So
yeah. Okay. So 1 minute. There are okay. What does it mean to be stable under the action of the group?
Right. So it's right. So yes. So I think so. So there is also an answer here, which I will just read out. For every element of the group, every element G of the group, and every vector in this subspace, G dot V must also lie in the same subspace. Okay. And I want to just sort of point out one thing. Okay, maybe we can do this later because I haven't really talked about infinite groups. But,
there are more questions.
Yeah. So so just notice one thing and try to see an example. If I have a linear action of G on a vector space, then the orbits of G in this vector space and the subspaces that are stable under the action of G are going to be in general very, very different things. Okay. So you can see this in some very small examples too. Okay. So is there another question here?
W being okay for every element. The last question was for every element of G of the group and for every vector V in the subspace, GV must also lie. So that is also an answer.
That was an answer to the previous question. Yes. Okay. Right. So we would like to have some decomposition like the orbit decomposition. By the way, I should say, I have introduced G actions on sets and linear G actions are two parallel things, and they are in a way formally, but please don't go too far with this. Right? In the two situations, the way they behave are quite different. Okay? Some formal similarity, that's all. Okay. So in the group action on a set case, the smallest things were orbits. So what is the smallest thing? And so the natural definition is that you call a representation irreducible or just a simple G module if it does not have any proper non-zero sub-representation. So notice that the zero vector space is of course stable, but we don't count that. And the whole vector space also of course is a sub-representation of itself. So it's the ones that are in between that I'm looking at. Right. So what are some examples of simple modules? Notice that every one-dimensional representation will automatically be simple, for example. Right. But we will see other examples. All right. So pushing this analogy further, what I would like to do for a group is that to classify
sorry,
all the
Upendra,
irreducible representations. Yes.
Upendra, just, I mean, when you say one dimensional, you mean the vector space is one dimension.
Right. So the dimension. So right. So when I use words like words that are purely linear algebraic to representation, they mean just as a vector space. Like for example, span, like linear span or dimension or subspace. If the G action is taken into account, then we will say things like G span or G stable. Right. The terminology will be appropriately modified. Okay. So one thing is I would like to identify what these atoms are for a given group. That is, what are, up to isomorphism, what are its representations that do not have any smaller parts in them. Okay, so we call them simple modules. So we would like to classify them for any given group G. And the nice situation is where we hope that the only way these atoms can be combined is in the silly way that we saw earlier, namely just by block diagonal matrices, just by taking direct sums. Okay. So this is the ideal situation that one hopes for. Okay. And it certainly does not always happen. But we are lucky in that many situations of interest, and in most situations of interest to us here, it does happen. Okay. So this is the theorem, that this desirable situation is always true when the group G is finite. And remember our blanket assumption that all vector spaces are over complex numbers. Okay. The way one proves this is by doing an averaging trick, which I will not get into. Yeah, and it is a useful thing to remember that the criterion of semi-simplicity, which means that every representation can be written as a direct sum of irreducible representations. This is equivalent to every sub-representation of a completely reducible representation having a G stable complement. One way you can see this fairly easily, if you have the latter property that every G stable subspace has a complement, then for a finite dimensional representation, such representation, I can simply induct on the dimension. If the given representation is irreducible, then I am done. Otherwise, there is a simple submodule. Take its complement. Then the complement will have smaller dimension. Find its subrepresentation if one exists, and so on. Right? The other way is not that straightforward. It's not difficult, but anyway, so this is an equivalent characterization of semi-simplicity. Okay, so now things become slightly interesting over here. So the orbits are unique. So you might say that if I write a G module as a direct sum of simple modules, then the simple constituent should be unique. That is unique on the nose, physically unique subspaces. And the thing is, they are not. Okay. You just have to remember, for example, if you take the trivial group, which is a one element group, then its representation is just a vector space. Because the identity element has to go to the identity matrix. So every vector space is a representation, and irreducible representations are just lines. And certainly there is no unique way to write a vector space as a direct sum of lines. So, okay. So, I mean, there is nothing subtle over here. However, what is interesting is that if I gather together all irreducible sub-representations that are isomorphic to each other inside a given representation, and I write their sum, then that is called an isotypic component. And that really is unique on the nose. Okay, so this is going to be important for us later on, not for a proof, but for the proof of a result, which I will quote. All right. And again, this is
one more question.
Yeah.
There's one more question in the chat. Are there partial or full analogs of representations of other objects?
Right. Why is theorem for Lie algebra representations? Yes. Yes. So for a semi-simple, complex semi-simple Lie algebra, you have complete reducibility. Yes, indeed. But not for infinite dimensional ones. Okay. So non-complete reducible situation is also very interesting, but it is not really that relevant for us. Okay. But again, see, the fact that these isotypic components are unique, it should not be that surprising, because let's say you have, because what are group representations? They're really just some operators acting on a vector space. So if I take a single operator, then the decomposition of the underlying space into eigenspaces is unique, even though there isn't a unique eigenbasis, right? If some eigenspace has dimension more than one, then you can choose a basis in any which way, but the eigenspaces themselves are unique. So it's exactly the same situation. Okay, but in order to see this theorem in action, we should really expand our, our stable of examples. So let's see some more examples in action, right? And for these examples, I'd like to remind you of what we did for groups acting on sets, where from a given action, I could have lots of other actions on subsets, lists, multisets, etc. So this is a similar situation. So if I have a G action on a vector space V, linear action, then G will also act on, so in math speak, G will also act on tensor powers of V, on symmetric powers of V, on the dual space. But really what is happening is very, very concrete. Okay. So if I think of this G action explicitly given by some matrices by means of a fixed basis of V, then I can simply take ordered pairs of such basis elements, and I can linearize the action, and I can take the formal span of those, and G will act also on that. I have to distribute, thinking of this ordered pair as some kind of a product. So I have to force distributivity. That's what the tensor product does. And similarly, so I can also take a basis as variables, and I can take monomials in those variables and think of that as a basis for something. So take the space of homogeneous polynomials of a fixed degree in variables that are basis vectors of the given space. And you can see that by acting linearly on each one of the variables, I may get a linear combination if I act on a basis vector, but I can simply expand the parentheses. Okay. So I will get an action. So this is what we call formally the symmetric power of the vector space. And you can also act on functions on V. So there is a little bit to check over here. So I have the action of a group G on a vector space V. So how do I act on linear functions on V? G acting on a function has to be another function. So I have to tell what it does to a vector. But G itself acts on a vector. So I could define it as f of G acting on that vector. This does not work because the left action gets switched into a right action. It becomes an anti-homomorphism. So you can check that putting this inverse here does the job. And now I'm restored to a homomorphism of G into GLV. Okay. Now, carrying this out in practice becomes more interesting. So remember that I already asked you to decompose the defining action of Sn on, an linearized n element set. So now I can take the second tensor power or the second symmetric power, or if you're adventurous, you can take higher powers, but it does become hard without knowing some theory. And then you can try to decompose these. I really do recommend this exercise. Okay. Right, because you can read what I have written over there, that such kinds of operations I'm told are quite useful in computer science. Okay. So everything until now was some kind of totally different beginning, in that it really did not connect in any way with what we discussed so far in algebraic geometry. So let's go back to that situation. All right, so I have given here a little bit of review. So remember that an affine variety is just the set of common zeros of a bunch of polynomials. Right? You draw their graphs and you intersect. It doesn't matter if you take the ideal, and it doesn't matter if you extract all the roots of this. So that's what radical ideals are. And then we saw that somehow if you have an affine variety, then knowing about this variety is really the same thing as knowing about the ring of functions on that variety. So you just take, because this variety, let us say it is realized in an affine space, then the functions on this variety are just functions on ambient space, the polynomial functions on ambient space, which are, polynomials in coordinate functions. And then you restrict it to this closed set. So which turns out to be precisely this quotient of the polynomial ring by the radical ideal. Okay. Yeah, and somehow this coordinate ring really captures completely the geometry. For example, maps between such varieties, that is regular maps between such varieties are captured by a ring homomorphism between their coordinate rings. Okay, so then after that we defined affine algebraic groups or algebraic groups, but we will concentrate only on affine algebraic groups, which means that it's an abstract group and it's also an affine variety. But the two structures have to be compatible with each other, which simply means that the multiplication map from G cross G to G and the inverse map from G to G, they have to be morphisms of varieties. So remember that G cross G has a structure of a variety, as was discussed last time by Raghavan. Yeah. So what we want to do is we want to now consider we want to consider representations of algebraic groups. But we do not want to consider abstract representations, because we would like this representation map also to be compatible with the structure as an algebraic variety. And so all that means is that this action map G cross V to V should also be a morphism of varieties. So remember, G was an affine variety, and V is a vector space. So it certainly is an affine variety. It's just the usual affine space. So both sides of this map, they are affine varieties, and we require for a linear representation, we require this to be a morphism of varieties. Okay. So I don't know about you, but if all of this was thrown at me in one go, then I'm definitely would not be able to digest this. So this is a lot to digest. But I've been told by KV that in some sense, we don't really have to worry about this too much, because really we care only about GLN. I mean, maybe that's a lie, but GLN and its close relatives, which are subgroups of the following kind. So here's a list. So the special linear group, then the group of diagonal matrices. Now notice that C star is also a general linear group, it's GL1. Okay. Then we want to consider groups of upper triangular matrices. Remember, invertible, because we are in a group, and only those upper triangular matrices that have ones on the diagonal. So these groups are useful in developing the theory, right? So, and products of such groups, or maybe quotients of such groups by finite subgroups. So, am I wrong here, by the way? Is this too rash a statement? If so, I'd like to be corrected, but this is my understanding, that if you care only about GLN at this stage, you won't lose much. And SLN. So.
Yeah. At this point, yes, certainly. I think that is.
Okay. So again, since we made so much noise about coordinate rings, etc., it's not a bad idea to actually write down the coordinate rings of these and really show that the groups that I have listed, they are closed subgroups of GLN. So for example, just to remind you, C star, if you just think of it, if you just embed it inside C, then it is not a closed set. But you can just go up one dimension and think of it as a subgroup, as a subset of the plane with xy equal to 1, and just look at the x coordinate. So you do the same thing for GLN using the determinant, etc. Okay. Now, this is a small point, but it's still worth saying. Now, remember, what was the sort of earlier way of selling a representation theory is that I want to study an abstract group, and there is no linear algebra, and if I can do linear algebra, I can always do more. There is much more elbow room. I can do a lot more things. So representation theory is a way to use linear algebra to study groups, and it has been tremendously successful. So you could say, well, GLN is already a linear group, so why bother, right? But the point is that's very definitely not the case. GLN itself is, it comes with its own natural representation, but I still do want to study its representations in other linear spaces, right? So I do want to study homomorphisms from GLN to some other GL. Okay. Now, this is also worth keeping in mind. I want this to be a map of varieties, right? It's not an abstract map. So, by the way, there are abstract representations of GLN that you can try to see how to construct one, which is not a rational representation. So what does it mean concretely that a representation of GLN should be a rational representation? And it means something very, very simple, right? The coordinate rings on both sides are simply polynomial rings in a square number of variables, and you're throwing in the inverse of the determinant, right? So all that it means, and then there is going to be a comorphism if this is to be a map of algebraic varieties. So all that it means is that if I take the coordinate functions in the target matrix, so m square functions, and if I pull them back, then there are going to be some functions of the n square entries of the source matrix, and I want all of these to be polynomial functions. I mean, strictly speaking, I'm allowed to take the inverse of the determinant, but I can really just multiply enough times by the determinant and really say that the entry should only be polynomial. Okay. So, and we'll see lots of examples of such things very shortly. Okay. So what I'm trying to emphasize here is that rational representation theory of GLN is a very, very concrete object. Okay, right? So one thing about these groups of interest is that many, not all of them, but many of them are reductive algebraic groups. So what does that mean? And there is a definition, but in some sense, we don't really care. So there is a structural definition which says that there should not be a unipotent radical. So there should not be any connected normal subgroup that is unipotent. But what we really care about is the fact that for these groups, I'm in the nice situation, the desired situation that I had sketched earlier, right? So you can even just take this as a definition of reductive algebraic groups over complex numbers. So what happens is that if I take rational representations of these finite dimensional rational representations, then these just break up into direct sums of irreducible representations, right? And GLN and SLN, they are definitely such groups, and their products, they are reductive groups. So now this brings in the question, what are the irreducible representations? That is, what are these building blocks? And the thing is that there is a very, very nice theory. All of these are serious theorems, but they are worked out a long time ago. There is an explicit theory. We know how to construct these irreducible representations, and they are classified by their highest weight. This is something that will get discussed. Okay. So we are just happy to accept these. And now an exercise. So notice that the group of diagonal matrices is something like that. It is just a copy of GL1. So you should try to show that this is a reductive group. Well, I did not define reductive. So what I mean by saying that is that all representations are completely reducible. Okay. And you really should probably use this fact, even if you cannot prove that Dn, all of those are diagonal matrices. But if they're acting on any rational representation, then it is a fact that each one of them will still act diagonally. Okay, this is not an obvious fact, but it is true. And the irreducible representations of the diagonal group are sort of the starting point of this highest fit theory. They're all one-dimensional, and so you should find them. Now, just in passing, This group UN, which recall is the group of all upper triangular matrices with ones on the diagonal. This is not a reductive group. And you should be able to find a counterexample, namely a specific representation that does not break up into, that is neither irreducible nor does it break up into direct sum of smaller things. Okay, and this again is not that difficult. So if you go by this analogy that I gave about eigenspace decomposition, then this is really saying is that if I have a matrix with a repeated eigenvalue, that if I take a generalized eigenspace, right, I need not have an eigenbasis. That's exactly what is happening here. So this is not something surprising. It's a okay. So are we doing on time? Okay. All right. So now this last longer exercise, this is something that I strongly recommend. Right? So how do I, so I said that GLN is important. So how do I, its representation theory is explicitly, concretely important for us. So how do I deal with those representations? How do I first generate these representations? And I already have the procedure. I already have lots of tools to do that. I start with the God-given representation, which is the defining representation. So GLN acting on the n-dimensional representation by matrix multiplication. Or if you want to think in terms of the homomorphism, then this is just the identity homomorphism from GLN to itself. But now I can bring my full multilinear toolkit to bear onto this and take symmetric powers of this, tensor powers of this, exterior powers of this, if you know what they are, and then ask a question, well, what will happen? So I strongly recommend this exercise, that try to see that the second symmetric power is an irreducible representation. See if you can say something like that about higher symmetric powers, third power, fourth power, and so on. Then take the second tensor power and try to decompose this into a direct sum of irreducible representations. So I want to remind you something in the first lecture where there was some kind of decomposition where there was the symmetric part and the antisymmetric part. Okay. Now that decomposition was only for the symmetric group on two letters, where there was only the switch. But some phenomenon like that is going to be happening over here. Right? And that's a hint. Okay. Now this last representation, this may look a little complicated, and it is. Okay. But you see, the multilinear gadgets that I have, I can apply them repeatedly. And such things grow in complexity very, very quickly. So what I have here is that I have the underlying vector space V to be C2. So the group is GL2, or if you want SL2. I have the induced representation on the second symmetric power of that. But this being a V on which SL2 acts, I can again take the second symmetric power and see what this action is. So I recommend that you go back and look at the first lecture. If you think of a basis of the underlying vector space as X and Y, then the second symmetric power, remember those are going to be polynomials in the letters X and Y of degree 2. So a basis of that is just going to be X square, XY, and Y square. And again, remember what the linear action is. The linear action is simply if a matrix sends X to something and Y to something, then I just plug those linear expressions into X and Y. Think of those as polynomials and just expand. Right? So if X is going to AX plus BY and Y is going to CX plus DY, then XY by means of some matrix. Well, you can even write down this matrix based on what I said. Then XY will simply go to the formal product of those, and I open the parentheses. Right? So something very, very concrete is going on. Right? Now, if I take the second symmetric power of this, then just take a moment to see what the dimension of this representation is going to be. This. Yeah, so just take a moment to see what the dimension of this plathism representation is. Just take a moment. So now I think of x square, xy, and y square as variables, and I take symbolically polynomials of degree 2 in those variables, right? So I'm taking polynomials of degree 2 in 3 variables. So the dimension of that is going to be, well, 6, right? I think the students will probably be better in this counting than me. All right. Now, strictly speaking, if you recall, there was some kind of switch over there, right? So ax square plus bxy plus cy square, a general vector like that, was identified with the tuple a comma b comma c in the first lecture, right? And there was a remark that there was some kind of duality happening. So the duality, if you want the math speak for it, is that I'm switching from x square, xy, y square to the dual space by taking the coefficients of a general vector. So that is what the star that is what the star next to this first symmetric power is doing, if you care about it. Okay. Yeah, so this is a very good exercise, which I confess I have not done. So it's an exercise for all of us, maybe except the first speaker, that that there is going to be an invariant in here, and so this is going to break up into two, a direct sum of two representations. All right, so yeah, so let's go back to the question, because we said algebraic groups, but really speaking, the major point of the last lectures is that what we want to study is the action of an algebraic group on a variety, and then study the decomposition of this variety into orbits. Okay, remember, these orbits are not linear things, right? Take, for example, just the very basic thing. Just take the action of C star on C, right? Just by multiplication. Or if you want, this is the identity this is the identity map from GL1 to itself. So this is a one-dimensional representation, but there are two orbits in there, namely C star and the vector 0. Right? So those are not linear things. So, right. So nonetheless, we went to all of this trouble to talk about representation. So my claim is that even if we care about in our study of orbits and studying their closures, which orbits lie in closure of which other orbits, we will be able to linearize the problem and then approach it using representation theory, right? So let's see some indication of how that might be. Are we doing on time? Okay. Yeah. So this is the idea. I want to go back and remind you of what we said earlier, that if a group G is acting on a set, then sometimes it is useful to consider functions on that set, right? So we are going to bring that idea back. Now, if the group acts on this variety X is really an infinite thing. So if I take functions on that, arbitrary functions on that, that's really just too big a thing, right? However, I already know that there are some good functions to consider on X. So I will restrict my attention only to those functions, namely regular functions. So suppose G is acting on this variety X, then G has a derived action on the regular functions. So remember that this C square bracket is the ring of regular functions. And this formula that I have written over here should be familiar. This is exactly the same formula that we had when we took the dual of a representation, right? Okay. Now, in this case, X itself, there is an action which is not a linear action. But when I take functions on X, this equation will still gives me a valid action. And now notice that this action is linear by sort of definition, because the way G acts on f plus g is, sorry, well, I can't say f plus g, g is a, so if I have two functions f1 and f2, then f1 plus f2 by definition is defined pointwise, right? By pointwise application. So this definition of action is going to mean that the way G acts on this ring of regular functions is going to be a linear action. So out of a non-linear action, I have gotten a linear action on this ring. Okay. However, keep in mind that this ring is going to be infinite dimensional. For example, if X itself is the affine space. So let us say X itself is a representation, right? N dimensional. Then this ring Cx is going to be the polynomial ring in n variables. So we have an infinite dimensional representation that we are dealing with, right? And we said that we generally want to deal with only finite dimensional representations, but we can easily get back to that situation in the following way. Okay. So the point is the following. If I fix a particular regular function f, and I act on that by G, then I will get a bunch of other functions, right? Now what I can do is I can take the linear span of such a thing. The group G is going to be infinite, and this ring is also infinite. So one might think that this will be an infinite object. And yes, of course, as a set, it is going to be infinite. But it's not hard to see that this is actually a finite dimensional gadget. So I take a fixed element, a fixed function G, I smear it around by the group action, and I close it up linearly just by adding, just by taking span, linear span. And the way one sees this is not difficult. So you can look at this in any standard book, but the way one does this is that, remember that G cross X to X is supposed to be a regular map. And that means if I take the comorphism of this, that means the homomorphism from regular functions on X to regular functions on G cross X, then I can explicitly write this down map in a symbolic way. And what this map being an action, what that means, I can interpret it in terms of this comorphism. And then you just sort of follow your rules. Okay, so this is a standard thing, which maybe we can see later on if there are questions, but right now I would like to go on. Okay. Right, okay. And not only that, further, okay. So the first two sentences that I have written here, they go under the slogan that this action of G on Cx is locally finite. But in fact, I can do more. What I can say is that I can linearize the action on X itself. And what that means is the following. I can realize X as a closed subvariety of an affine space. I can define an action of X on this ambient affine space in such a way that that is a linear action. Okay. I strongly recommend that you do this by doing something very simple. Like, for example, I mean, just see this. For example, if you just start with a linear action to begin with, then this is going to be trivial. But let's say you start with a linear action. You take an orbit in the second symmetric power or something like that. Then this procedure is not really very difficult to carry out by hand. If you take a small concrete example. And so what this does is that this opens up the path to study orbits by using representation theory or, linear algebra. Okay. So I'd like to end by seeing an explicit example of what this kind of thing, what kind of payoff we can get from this kind of thing, which will also be preparation for things that are coming ahead about quotients. So we go back to our trivial representation. So the invariants for any representation of a group G, I can define the invariants to be the smallest, the largest trivial submodule contained in that. And this is exactly what is written over here. So I take all those vectors on which every group element acts trivially. That means acts by identity. And notice that this condition, because G action is linear, this is going to be a subspace. Right? It's going to be a sub-representation on which the group acts trivially. Okay, so I want to apply this idea to the G action on the ring of regular functions of a G action, right? And so I call this the ring of invariants. Again, notice that if two functions are invariant, then their product is invariant just because it is, because product is defined pointwise. Okay. All right. So I have obtained a subring of this ring of invariants. And now I claim that this subring is an extremely good thing to think about. So why is that? And this is closely related to our stated desire of studying orbits of the group action. All right. So it's a standard thing in mathematics right from the beginning that whenever there is an equivalence relation, we want to study the equivalence classes. So that's what orbits were. Now, in case of this geometric situation, we hope that the set of orbits is not just a set, but that itself has a geometric structure. And we would further hope that when I'm starting with an affine variety, X on which G acts, then this quotient, the set theoretic quotient itself will be an affine variety. Okay, so this is going to be a series of hopes. Okay, and they're not all going to be realized all the time, but still something nice is going to come up. Right, so let's just go on. Right? Okay, so let us assume that there is such an affine variety. So how do I look for this affine variety? Well, we know that an affine variety is completely characterized by its ring of regular functions. So we should look for regular functions on this variety, right? Now, this quotient just as a set, if I think of arbitrary functions on the quotient set, then it is precisely the set of functions that are constant on every orbit of the group action, right? But I don't want all functions. I want things that I want to designate as regular functions. Now, what better place to look for than the regular functions on X itself? So I look at the regular functions on X and I simply take those functions that are constant on orbits. Now, you look at just the definition over here, up here in the previous slide. What does it mean that a regular function is constant on the orbits? That means that this function f should take the same value on every x as it takes on any g dot x. But that is precisely saying that the induced action of the group on that function should leave that function fixed. Right? That's exactly what this equation, the displayed equation over here, is telling us. Okay? So in other words, a good place to look for this hope for a affine quotient is to say that I should take the affine variety. I should try to define this quotient as, or I can try to define this quotient as the affine variety associated to the ring of regular function, the invariants in the ring of regular functions. All right. So this is an excellent reason to study this. And notice what will then happen. Okay. So given any equivalence relation, there is of course the quotient map from the original set to the set of orbits. And now in this way of doing things, if everything works out the way we hope, then this map, which will now be a map of affine varieties, will simply correspond to the inclusion of the invariants into the entire coordinate ring. Right? So this all sounds very nice, and it is, but it doesn't work that easily, as further lectures will sort of discuss. But there is one sort of clear question over here, which is, just to get started, this ring of invariants that I have, it should be a finitely generated ring. it should be a quotient of a polynomial ring in finitely many variables. And so that should be generated as a ring by finitely many invariant functions. So that's the question, right? Because if this ring is finitely generated, then it is a quotient of a polynomial ring by some ideal. It is a fact that every ideal in a polynomial ring has finite number of generators. So I can hopefully explicitly find such generators. And then I actually have geometry associated with those. I can take the zero set of those and I can really do geometry. Okay? So this is really a worthwhile endeavor if if it is going to go through. So the question is this ring finitely generated? And the answer is yes, if we are in the desirable situation. Okay. So this is the theorem that if I have a reductive group acting on an affine variety X, then the ring of invariants is indeed finitely generated. So in particular, this is going to be true for GLN or SLN or all those, all the nice groups that we listed. If they're acting on an affine variety, then the ring of invariants is going to be finitely generated. Okay, so do we have time for proof? Okay, so we have some time. Yeah. So the proof of this theorem is a bit long, but it is very nice. And let me just sketch the steps and let's see if we have time to discuss the details. So one thing to recall, okay, so here. So a crucial thing in this proof is something called a Reynolds operator. So let us see what that is. Okay. Now, the coordinate ring has, as we saw, a locally finite G action on it, right? And the ring of invariants in that is a sub-representation. Because the group is reductive, we know that every finite dimensional representation is going to be completely reducible. We also know that this Cx is going to be made up of these finite dimensional pieces. So what we do is we take one such finite dimensional piece and we take invariants only from that. If you recall, one of the characterizations of complete reducibility was that every sub-representation will have a G invariant complement. That's just another way of saying is that given a representation V and a sub-representation W, I have a G invariant projection from V to W. Right? So I will be able to create a G linear projection like this, not yet from the entire coordinate ring to invariants, but from a finite dimensional piece to the part that is invariant in that. Okay. All right. So, but what happens is that all of these finite dimensional pieces, they are nicely put together. And so if I have a good operator, then I will be able to patch these operators together to get such a projection. But there is one more issue over here. So remember that the decomposition into irreducibles in any completely reducible representation is not unique. Again, just remember a vector space decomposition into a basis. Right? However, we said that if I take an isotypic component, namely I put together all the representations that are isomorphic to each other, then such a thing is unique on the nose. It is intrinsic, which is exactly the situation over here, because invariance is simply the sum of simply putting together all the trivial representations. So this projection operator, not only does it exist, it is a unique G invariant projection. And I will be able to put all of them together for the coordinate ring to get such a projection. Okay. Now there is one more nice property of this operator, which we require, is that this is not just G linear, but it is linear in the invariants themselves. Okay, so what this means is that if I take a function f multiplied by an invariant, let's say f prime, and then apply the projection, That's really the same thing as first applying the projection and multiplying to F and then multiplying by the same invariant. Okay. So this is not a difficult thing. One can see this by saying that any such projection operator onto an isotypic component is going to be compatible with G linear maps. Okay. This, along with the fact that multiplication by an invariant is going to be a G linear map from this coordinate ring to itself. Okay. So this is a small thing. There is nothing difficult over here. So these are the tools that we require. And now it becomes very nice. Okay. Okay. So this second point we already discussed. So then what we do is that the next step is that we reduce this proof from an arbitrary affine variety with a G action to a linear action. And remember that we already put this into place, that every affine variety on which G acts morphically can be put as a closed subvariety inside an affine space on which G is acting linearly. So in this case, what happens is that the coordinate ring of X is simply going to be a quotient of the polynomial ring corresponding to the ambient space. And the coordinate and the invariants of the respective rings will also be a quotient. So using this compatibility, I can simply reduce this finite generation to the case of when X is an affine space V on which the group G is acting linearly. Now, in this case, the coordinate ring is just a polynomial ring in as many variables as the dimension of my representation. And what I have to show is that the ring of invariants over here is finitely generated. Okay, but now I have an extra ingredient here which I did not have earlier. Is that symbolically, this is, I mean, I can regard x1 up to xm as symbols and I can track their degree. So every polynomial will have a degree and I can break it up into its homogeneous components. So I can do some nice symbolic work, and it opens up the possibility of induction by degree. So one observes that the ring of that this ring is graded and that the ambient ring is graded, and the ring of invariants is also therefore going to be graded. You get started by the fact that the only that in degree 0, the coordinate ring as well as the invariant, the coordinate ring is only one dimensional, it's just scalars, right? So that's the only thing that is there in invariants. So you get started over there, and then you use a bootstrapping argument using Hilbert's earlier theorem that every ideal in a polynomial ring is finitely generated. So this is a finite generation of ideals. So using these ingredients and a very nice but very simple argument, you can reduce finite generation inductively on the degree and complete the argument. Okay, so I have only 5 minutes left. All right, I think I will just stop here. And maybe we can have a discussion.
Yeah. So are there any questions you have for Upendra?
Yeah. So at the risk of flogging a dead horse, the exercises that I gave in this presentation, I will share this presentation once I'm sure that I didn't make any mistakes. So the exercises that are in here, especially the calculation exercises, I really strongly recommend that you do them. Especially the representation theory of the general linear group, how it works, how the multilinear algebra works. It is a very good thing to get used to that, because the irreducible representations, both for the symmetric group and the general linear group, they are really built using these kinds of operations. So there is one